Section 8.3 deals with trig substitutions. The goal in this section is to rewrite integrals that contain radicals and polynomials in quadratic form into something trigonometric that we can evaluate. So what we're looking at is replacing the variable in the integral with a trig function and rewriting the integral into something that we can evaluate, because the integrals that we're going to be looking at won't be in basic form and will not be something that we can do using a U substitution or integration by parts. So let's look at just a review of the right triangle definitions of our trig functions before we look at the substitutions that we most commonly make. So I just want you to recall that given a right triangle with theta being in this angle, that this is considered the opposite side, adjacent side, and the hypotenuse. So the sine of theta is defined as opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And here are the definitions for the reciprocal functions as well. What we're going to do, as I mentioned before in this section, is to look at an integral that contains some kind of polynomial that's in quadratic form, and we are going to rewrite it and replace the variable in our integral with a trig function. So there's three trig functions that we're really going to be using. The first is the secant of theta, the second, sine, and the third, tangent. What we have to do is look at the integral that we're given and determine, hey, which one of these should I let my variable equal? Well, the way that you do that is to look at the given. Well, if we end up with a radical where it's variable squared minus number squared, this is going to be where u is equal to a variable and a is equal to some constant. In this case, we're going to let u equal a secant of theta. So when we end up with something where it's variable minus a number, our trig function that we use to substitute for our variable will be the secant. Then we are going to build a triangle from here. So solving for secant, I'd get that u over a is equal to the secant of theta. And then if, again, this is my right triangle, we know that the hypotenuse would equal u, the adjacent side would equal a, and then using the Pythagorean theorem, we'd end up with this opposite side being u squared minus a squared. If we end up getting something that is a number minus a variable, so again, this is going to be where a equals some number and u is equal to some variable. In this case, our substitution would be for the sine. So we would let the sine of theta be what we replace the variable with. So looking here again, solving this for sine, we'd end up with u over a is equal to the sine of theta. And we'd use this to build our triangle. Again, if this is theta, u is the opposite side, a would be the hypotenuse, and the adjacent side using Pythagorean theorem would become a squared minus u squared. Finally, the last one, if we end up with something that is a variable squared plus a constant squared. So again, this is going to be where u is equal to a variable and a is equal to some constant or some number. We would let our substitution be for tangent. We would replace our variable with tangent. So again, solving this for tangent, u over a is equal to the tangent of theta. And setting up our triangle, again, if this is theta, u would be the opposite side. The adjacent side is a. And using Pythagorean theorem, we'd get that the hypotenuse is the square root of u squared plus a squared. So we will again be looking at three different substitutions: secant, sine, and tangent. And the substitution that we use depends on the given. So if we're given variable squared minus constant squared, our substitution will be secant. If we're given number squared minus variable squared, our substitution will be sine. And if we're given variable squared plus a number squared, our substitution will be tangent. So the most important part for trig substitutions is identifying the given as one of these trig functions. So let's look at example 1. We need to evaluate the integral of 3 divided by the square root of 1 plus 9x squared. Well, if we look here, well, that looks like variable squared plus constant squared. So this means that our substitution will be for the tangent of theta. Again, because it's variable squared and constant squared. So if they're added together, variable squared, constant squared, we're looking for a substitution of the tangent. So let's identify what everything is, because here again I have u squared and a squared. So here I know that u squared is equal to 9x squared, and I know that a squared is equal to 1. So a would be 1 and u would be 3x. Following our formula here, I need to let u equal a tangent of theta. So in our case, we would say that 3x is equal to a, which is 1, times the tangent of theta, or 3x is equal to tangent of theta. So this is the substitution that we will be making to rewrite our integral into something trigonometric. We're going to go ahead and build a triangle for this right now. So if this is our triangle, and this is theta, and we're looking at the tangent of theta, we know that the side opposite would be 3x. Since there are no denominator, we're assuming 1. The side adjacent is 1. And then again, if you just used Pythagorean theorem, we'd end up with this side right here is going to be the square root of 1 plus 9x squared. We want to, again, transform this entire integral from something in x to something in theta. So I'm going to rewrite it over here, and we're going to look at it as the integral of 1 over the square root of 1 plus 9x squared times 3 dx. So I know I need to replace the square root of 1 plus 9x squared, and I also need to replace 3 dx in this problem. Well, looking at my triangle, here's the square root of 1 plus 9x squared. So I want to know, what is the square root of 1 plus 9x squared equal to in terms of a trig function? Well, when you're determining that and looking at your triangle, make sure that you're only using the side with the algebra that you need, and then the other side that includes the constant. So never reintroduce the variable into your problem. So I'm looking at this triangle, and I know that I need to rewrite the square root of 1 plus 9x squared as a trig function, and I have theta here, so I need to relate it between the hypotenuse and the adjacent side. Well, I know that the secant of theta is equal to hypotenuse over adjacent, which means that the secant of theta in this case would equal the hypotenuse, which happens to be the square root of 1 plus 9x squared, over my adjacent side, which is 1. So secant of theta is equal to the square root of 1 plus 9x squared. In my problem here, I know that instead of writing the square root of 1 plus 9x squared, I can write secant of theta. Then I need to replace 3 dx. If I look here, I let the tangent of theta equal 3x. Well, the derivative of 3x is 3 dx. The derivative of the tangent is secant squared theta d theta. So if I want to replace 3 dx in my problem, I know that from the substitution that I've made, 3 dx is going to equal secant squared theta d theta. So I replace this with secant squared theta d theta. So now I have a new integral, and my integral is 1 over the secant of theta times secant squared theta d theta. Well, this is something that I can evaluate. I look at this and I know that one of my secants will cancel, so I'm just looking at the integral of the secant of theta d theta. That again is something that I know how to integrate. The integral of the secant theta of d theta is equal to the natural log of the absolute value of the secant of theta plus the tangent of theta plus c. Then what I need to do is replace my secant of theta and tangent of theta with what secant and tangent are equal to in terms of x. We do that again by looking at the triangle unless we've already found that answer somewhere else. I know what the secant of theta is because I've already found that the secant of theta is equal to the square root of 1 plus 9x squared. But if I didn't know that, I could go back to my triangle and say, well, secant is hypotenuse over adjacent and determine what the secant is. So I know I need to replace secant of theta with the square root of 1 plus 9x squared. Then I need to figure out what the tangent of theta is. Well, I've already determined that the tangent of theta is equal to 3x. But if I had not already determined it, again, I could use the triangle to determine what the tangent of theta is. I know tangent is opposite over adjacent side, so either way I look, the tangent of theta would equal 3x. So now we're back in x's, which means that the integral of our original problem, which was 3dx over the square root of 1 plus 9x squared, is equal to the natural log of the absolute value of the square root of 1 plus 9x squared plus 3x plus c.